you so much all for being here today to see my presentation for the Artium MP seminar. So I would like to start with acknowledging all the team and researchers that I work with, which I will present the data today from. I did my PhD in Dima Perpichka's group at McGill, and traditionally trained as a physical organic chemist working on organic semiconductors, solid state chemistry, so to say. And I did a postdoc after that with Professor McLaughlin at UBC, working on supramolecular chemistry. And now this is going to be mostly the presentation that I'll have today, my postdoc and PhD story and journey. And now I started my own group since last year. My first PhDs arrived 3 months ago. They're sitting at the back here. So the research lies in the hands of the young generation now. I'm starting to get old, so to say. So I'll go through how a serendipitous discovery of a phosphorescent solid started my journey as a PhD. And then how I worked on different methods of synthesizing porous covalent organic frameworks. And that sort of synthetic method allowed us to make the first phosphorescent COFs. That was sort of the whole package of my PhD thesis. And then the same methodology that I worked in my PhD also allowed us to work on a macrocycle, sort of an impossible or difficult macrocycle that I synthesized in my postdoc. We just submitted the paper recently. So starting with phosphorescence. Phosphorescence discovery dates back to ancient India and China, where there were reports of stones glowing all night long in the mountains. And people believed that they were a part of moon that has fallen on Earth. They called them, so to say, moonstones. But today we know phosphorescent afterglow emission is not from the moon stones, but rather when you excite a molecule from the ground state, it goes through a singlet excited state, the same sort of preserved spin. And if the singlet excited state emits back to the ground state radiatively, you generate fluorescent light, normally spontaneously in nanosecond lifetime. But if it goes under an intersystem crossing, it will flip the spin of one of these electrons essentially to generate a triplet excited state. Now this triplet excited state is a metastable species, and that will not decay back to the ground state. It will stay for a long time until it does another intersystem crossing to the ground state. So giving this afterglow essentially as the phosphorescence. And the main difference essentially, the most important characteristics difference of fluorescence and phosphorescence is the spin of the systems, the two excited states, and the lifetime at which they are going to emit, right? One being spontaneous, one being in microsecond to second regimes. And these two characteristics brought a lot of applications. Of course, we want to see afterglow for this glow in the dark toys and artworks, and you probably have seen it on the planes. When it gets dark, you see all these notices starting to glow at night. And for anti-counterfeiting, for bioimaging, where you can have fluorescence, background gone, and phosphorescence code or the stain systems start to show up. But also the triplet manifold allows us to harvest more excitons from our LED and conventional LEDs. In triplet qubits and triplet lasing, many quantum applications that arise from this triplet nature of the compounds. But organic compounds or organic materials don't like to phosphoresce, and we have to sort of design them to be phosphorescent in many cases. The first obstacle that we have is how to generate triplet excited state, how to do this spin flip essentially, so to say. And to enhance the intersystem crossing rates, we either need to embed heavy metals inside, normally iridium, platinum, or add functional groups with N to pi star moieties to enhance this intersystem crossing through a change of orbital momentum and generate these triplets. Once the triplets are generated, then we have to preserve them from all sort of different pathways that could decay and not allow any phosphorescence emission for us. For example, triplet annihilation. Two triplets would like to meet each other, one going to the high-lying singlet excited state, one losing energy down to the ground state, right? Oxygen is a triplet state. In its ground state, the oxygen gas is a triplet molecule that will react very prominently with triplets that would generate. And of course, non-radiative decays in microsecond to second lifespan of these triplet excited states become really important as well. So we have to cool it down either to cryogenic temperatures or very solid matrices, and also normally dilute them in a matrix so that these triplet annihilations don't occur as well. And you can see from this design principles that making an organic compound phosphoresce at room temperature without heavy atoms is going to be really scarce and difficult to do. And it was until the works of pioneering works of Benjamin Tang and Wei Huang in the field that people started to see these phosphorescent pure organic crystals showing and appearing more and more in the literature. But still, most of them at the time that I was a PhD were suffering from very low phosphorescence to fluorescence ratio. So yes, we could see the afterglow in these pure crystals, but you can see, for example, this tiny little emission of phosphorescence in the baseline in 500 to 600 region as compared to the fluorescence. So the intersystem crossing is still not very efficient, even though now we could observe. And they're very scarce. And all this leads to lack of rational design. You can't say at the time, you couldn't say, I want to make a red phosphorescent compound in the lab, and you go and make a molecule that's phosphorescent in its solid state with red emission, right? So this is where my PhD started. I worked on this tribromo as a triangulin trion molecule, short for TB Tango. And that was a whole different project that I wanted to do with it. With Federico Rose at the time in INRS, we made mono layers of these 2D polymers. We studied their semiconducting behavior, their Dirac cone behavior, et cetera, et cetera. But I found that the precursor itself in its crystalline state is highly luminescent, which for an undergrad who just started the PhD in 2017 was something bizarre for me, because I learned in my courses that organic molecules, especially flat molecules with carbonyls and stuff, in their solid, they're normally non-emissive because of aggregation cost quenching. So I started digging into the literature. What could be the origin of this luminescence for this compound, as a matter of curiosity at the time? And I found this nice work by Kim et al., where they presented a co-presence of carbonyls and bromines having halogen interactions in the halogen bonding in the crystal, enhancing phosphorescence of such systems. I looked at my molecule. I said, okay, I have bromine, I have carbonyl. You know, we're getting somewhere with this. It might be actually phosphorescence. So normally, as a organic chemist, I went to the lab, made a bunch of different derivatives to study how this bromine presence is affecting the luminescence. I made different halogens, so chlorine, bromine, iodine, a non-substituted version of Tango, and a tertiary butyl version just for the sake of solubility. These were very flat molecules, not dissolving well. And the ones that I could dissolve, they looked in solution all almost identical. Substitution was not really changing much of emission. They're normal organic fluorescent dyes. But it was in the solid state that the changes started to appear. In the solid state, I could clearly see that all the halogenated derivatives were highly phosphorescent. The non-substituted Tango was phosphorescent, but the tertiary butyl Tango was not. Here you see the black emission. It's the total emission. You shine light on the sample and you collect whatever light that comes off of it. In the red, you see a delayed emission where you shine light, you wait for normally a microsecond or a millisecond, and you start collecting the light that comes as an afterglow. So you eliminate all the fluorescence of the system. But this was striking for us. They looked identical in solution. In solid, the tertiary butyl doesn't seem to be phosphorescence. why would it be, right? Like that. So I looked at their crystal structures. We were delighted to see that they're actually all packing roughly the same in their solid state, having this nice columnar pi stacks sitting next to each other because of the flat nature of the molecules. And it was only in case of the tertiary butyl tango where the molecules were rotating 60 degrees on top of each other to accommodate for this steric hindrance of tertiary butyls, but still have these flat pi stacks dominant in their crystal structure. So this rotation, that change in the luminescence of the solid versus the rest that were face-to-face packing, we wanted to see why is that. So I started looking at very basic density functional theory. I cropped a dimer of tango from a crystal structure and started rotating them in the software on top of each other and looking at the oscillator strengths of low-lying singlet excited state to the ground state, right? And what it tells us, this oscillator strength, is how prone that excited state of the dimer is to have a fluorescence emission. We could see that in case of the rotated dimer, the 60 degrees, it's reminiscent of the tertiary butyl tango dimers in its pi stack. It has the highest oscillator strength, meaning that when we excite the molecule to the ground, to the excited state, the singlet excited state that is generated is highly radiatively going back to the ground state to emit fluorescence light, whereas the non-rotated system, where it's reminiscent of the halogenated or non-halogenated derivative, that has very low oscillator strength, meaning that when you excite it, it generates this singlet excited state, but it doesn't want to radiatively get back to the ground state. It just stays there until some other pathways like the intersystem crossing or non-radiative decays would start to consume it. And that's probably how we got phosphorescence in this system. So I got greedy. I said, okay, now we found the design principle, changing the substituent, looking at the emission. Let's try this with other derivatives as well. So I started working on 1/3 of tango molecule. That's acridone moiety. Acridone is very bioactive. It's present in many drugs. So I was like, let's see if this will become a phosphorescent crystal and we can design phosphorescence now, engineer it, if we have enough tools to do. So I started making a variety of different derivatives of it, different sterics, different electronics, and I started looking at the emissions, and it was just too difficult to understand or find sort of a system that they are showing this photophysical behavior. And we found that it's not complex because the photophysics are complex. It's complex because we have no control over how they're packing. A tiny change in the molecular substitution is just having a totally different crystal structure, some of them being polymorphic, making different crystal structures on their own as well, each having different emissions. And we started thinking about maybe that's why we don't have a control over this excitonic behavior in such solids for the phosphorescent compounds. What if we could design the topology or molecular interactions of these solids from the ground up? I was at the time working on covalent organic frameworks in Dima's group, and covalent organic frameworks are essentially these 2-dimensional or 3-dimensional polymers similar to MOFs, if you're familiar with them, where just knowing the symmetry of the building block and how they're gonna interact with each other, we can predict what's the topology of the solid that we're gonna make in our reaction, essentially. And the main, the most important, essentially, trait of making a covalent organic framework is to use reversible linkages. Because if we take normally a symmetric molecule or two and we try to react them, what we end up, if we have an irreversible reaction, is just a messy polymer, non-crystalline, amorphous, right? We still don't know what sort of molecular interactions are there. Is there pi-pi stacking? Is there not? But if we use reversible reactions, what happens is this amorphous phase that forms, it will do exchange reversibly until it does a lot of error correcting mechanisms to generate a crystalline framework as the most thermodynamically stable phase for these compounds. For example, if we take a C2 symmetric building block, we use boronic acid condensation, which trimerizes these boronic acids. We put it in a reaction vessel, we heat it up, we will generate a hexagonal topology of covalent organic frameworks, which each one of the corners have one of the same, essentially, each one of the vertices have one of the same building block that we started with. If we take a C3 symmetric building block and a C2 symmetric building block, for example, this sort of transformation is called dioxaborole transformation. It's still reversible. We can make another type of Kagome lattice where now in each one of the corners you have a different precursor, in each one of the axes you have a different. I looked at the molecule we had. Tango is symmetric, planar, and we could easily think of ways to make covalent organic frameworks with it. So why not making such a COF? And because in most covalent organic frameworks, pi-pi stacking is face to face. In their crystalline phase, we would expect them to be actually highly phosphorescent as well. I started making boronic acid derivative of tango to make COFs, obviously. And what I noticed was that when we had this B-pin groups, sort of both from the synthetic perspective and for the solubility and easy purification, they were very easy to work with. But as soon as I took the B-pin off to make the bare boronic acid to make the COF, it just turned into a highly insoluble, impure mess that we could not form anything with it. So the idea was, why not taking this protected boronic acid and form a COF with it, right? No reports at the time for very obvious reasons if you know boronic ester condensations, because this B-pin is very, very thermodynamically stable. It's difficult to get it off and install another sort of catechol or di-O moiety on top. So I was looking for different reactions that in principle, we would add something in there that can take the B-pin off for us. B-pin is this red group over here. And we would be able to release the boronic acid and in situ form a polymer. That would be the ideal scenario, because we didn't want to get the boronic acid separate and purified. But many of the condensations, the reactions at the time required very harsh oxidants, very harsh acids, reducing agents. It just didn't seem to be viable to have all these very harsh chemicals with our phenylene diboronic acid for 3 days in the oven, right? I tried it, believe me, it just gives a black mess for many of these. And it was until I found this very elegant work by Hinks and Klein. The paper the title is The Virtue of Volatility. And what they did, they used this genius method to use methyl boronic acid as a mediator. And what it does is it will be in exchange with the pinnacle here to release the boronic acid, but it's a reversible reaction. So by adding a lot of this methyl boronic acid into the system, and then evaporating that methyl B-pin that comes off of the reaction, we can in principle drive the equilibrium all the way to get the methyl B-pin out and release the boronic acid for further use in our system. So I started doing the same methodology, just add methyl boronic acid, a little bit of acid or base or no catalyst, and then started having polymers inside my reaction vessels. When we look at the powder X-ray diffraction of these polymers, we found that they have identical phase to the COFs that have been reported with no protection on them. So now we could make COFs from the BPN derivatives of aryl boronic acids. And most of the COF reactions, they just produce a nanocrystalline powder that we cannot do single X-ray crystallography on them. So we look at powder X-ray diffraction, and the first peak usually is reminiscent of in-plane order for us. So that shows essentially pore-to-pore distances. And the last peak is the out-of-plane periodicity. It's in most of 2D COFs is the pi-pi stacking, right? The closest crystalline that we have in that system. So I started thinking about another type of transformation. Why not trying to add a linker, another linker, and form a different type of covalent organic framework, right? But we were able to make the same thing. We identified that the phase is identical to the COF that is made from the bare boronic acids. So this method works. This methyl boronic acid, so to say, transesterification works for the dioxaborole transformation as well. But that was very inconvenient to work with because now we had 3 precursors to add into a reaction vessel in small amounts. That's really difficult to do. And this hexahydroxyterphenyline molecule, it has 6 hydroxy groups on a pi conjugated core, is very insoluble, highly oxidative and unstable on bench. Essentially, even if you buy it from companies, you open it in the glove box, it's already gray. And you just put it on the bench for 2 days, it just polymerizes and oxidizes into different species. So I started thinking, why not connecting the deprotecting agent, this methyl boronic acid, to the catechol moiety? We protect essentially our catechol from all these oxidations. We turn it into a single precursor that can get the pinnacle off for us through this methyl boronic acid. And this catechol, this hexahydroxyterphenyline, would be able to go and link the precursor for us. And the product of that is indeed a very soluble compound, highly stable on bench as well. And to our delight, that idea worked as well. So now we had a single precursor working both as the deprotecting agent and the linker for us. But what we noticed is it's fundamentally different from the bare boronic acid and bare catechol reaction because that's a condensation reaction that occurs in case of the conventional synthesis. There's going to be water forming during the condensation, right? But our methodology was a double displacement. We had methyl boronic acid reacting to get the pinnacle off and going to the gas phase, and then phenyl boronic acids getting the hexahydroxyterphenyline to form the COF. So there is no water forming. In principle, not only we solve the solubility of both the catechols and boronic acids, now we solve another fundamental challenge of being able to do reactions water-free, so to say. So we made a scope of the COFs to show our method is really general, not working with the phenyl boronic acids only, but 2 particular cases we chose to show the fidelity of our methodology. One was a pyrene tetraboronic acid, which is a very insoluble molecule. No one has made COF before with this compound, even though pyrene diboronic acid was overexploited to make covalent organic frameworks. That's because it has the same issue as the Tongo, essentially, being a very insoluble and impure boronic acid to work with. But using the pinnacle, we could synthesize a nice crystalline COF, just like the other COFs that we reported. And the second case was a tetrahydroxy diboron precursor. And it's fundamentally impossible to make this COF using conventional reactions because this boron-boron bond is highly susceptible to water attack and forming borax. So even in the most anhydrous conditions that we could work with, as soon as the reaction occurs with this catechol, essentially the boron gets connected to these 2 oxygens, there's going to be 2 water molecules released, and this release of water molecules would break the BB bond. But using our methodology with the B pins, now this problem was solved. There was no water releasing. It was the methyl pinoculate ester releasing into the reaction, which was inert to these conditions. And we made the first tetrahydroxy diboron-based covalent organic framework as well. And later, we studied the kinetic of the COF formation using solution state NMR, because now we had NMR identifiable precursor that was essentially getting released into the reaction. We could track the formation of this methyl pinoculate ester and essentially track the covalent organic framework formation. But also, we use the same methodology to make mechanochemical solvent-free covalent organic framework formation. And we studied many different techniques. We found that even just crushing the powders with a hammer, sort of like a caveman, it forms the covalent organic for us. So we don't need really very fancy techniques like ball milling and RAM to make COF solvent-free. Long story short, we went back to the original idea. Now we were able to make the Tango COF. But it turned out to be totally non-luminescent. Essentially just dark yellow sad powder, so to say. And we found that I neglected the electronics of the system when I designed it, because we had this very electron donating tetrahydroxy benzene in the center as the linkage, and the electron withdrawing Tango core, which has 3 carbonyl groups, 3 boronic acid groups. And when we excite this system, the electrons would flow from the electron donating core, HOMO, to the LUMO of the electron withdrawing core. And having this charge transfer excited state is totally non-luminescent for us. But I had a lot of COF1, this phenylene diboronic acid condensation, because I used it for my model compound reactions to do the transesterifications, if you remember. I had a bunch of it laying on the bench. I thought, let's see what sort of luminescence this compound has. Surprisingly, no one studied the luminescence of this COF. It's the first COF reported in 2005 by Omar Yaghi in Science paper. And after 20 years, no one looked at this luminescence for us, which was very surprising. It looked like very luminescent COF. So nothing interesting, so to say, about this. It's a fluorescence framework. But when we looked at the delayed emission, we found that it has a tiny, tiny bit of phosphorescence. You can imagine this peak being somewhere down here in this is normalized, right? Being somewhere down here in the background. So it had a little bit of delayed emission somewhere there that we could, in principle, enhance by adding something heavy into this framework, right? So I started designing the dichloro and dibromo version of this phenylene diboronic acid to see whether we can enhance the phosphorescence emission now through heavy atoms. Well, it didn't work with many trials, probably because of the steric hindrance of all these halogenated derivatives kind of cramping inside the cavity of the COF and not allowing the COF to form or have proper pi-pi stacks anymore. So I took a step back. I thought, we can make COF1. What if we dope it with some of these halogenated precursors? We can still form the COF. Presumably, it will stay crystalline, especially in low doping percentages. But we covalently dope this framework with these halogenated precursors, not only to enhance the intersystem crossing and providing a rigid matrix for these halogenated precursors to have less vibrational decay, but also we dilute them inside this framework so that the triplets cannot meet each other and annihilate each other anymore, right? Well, I went ahead with the synthesis. We made a series of different doping concentrations, looked at their crystallinity, making sure the phase is still observed. The amount of dopant could be easily identified by the high resolution XPS as well, because boron orbitals and halogen orbitals look surprisingly close in the XPS, and we looked at homogeneity of the halogens inside these particles, just to make sure we don't have a chunk of highly doped COF and a chunk of non-doped COF. Well, they were phosphorescents. We could see clearly that the more chlorine we add to the system, the more phosphorescence it starts to appear. And this is much more pronounced in case of bromines, because of course it's a heavier atom, the intersystem crossing grows faster in the system. But one thing that was unexpected for us, maybe a little bit expected, was that originally the more we dope, the more phosphorescence we get. But then at some point, of course, we're generating more triplet excited states. The phosphorescent quantum yield starts to decrease quickly. So that brought us back to this idea of triplet annihilation. Maybe we should have like an optimal doping concentration where we generate a lot of triplets, but not too much now that they start to annihilate each other. And we were lucky to see something called a delayed fluorescence, which is an indirect way to talk about triplet annihilation. As I mentioned before, when you have two triplet excited states, when they meet each other, one of them loses the energy down to the ground state, and one of them gets pumped to high-lying singlet excited state. This singlet excited state can then come back through internal conversion to S1 and emit a fluorescent light from S1 to S0 if we have a fluorescent COF. And this fluorescent light is fundamentally different from the regular fluorescent, the conventional fluorescent, because it's gone through two triplet excited state, a bimolecular process, a much longer process. So we see it as a delayed fluorescent. It's not a nanosecond regime anymore. It's really a millisecond, microsecond. And if we map this delay fluorescent ratio to the phosphorescence peak that we have for a particular intensity of light that we were using for the COF, we found that we get a nice, almost linear correlation with the doping. The more you dope, the more delayed fluorescence you have, which is an indirect way to say that the more triplet annihilation was occurring. So it's really a game of balance in such systems. Of course, they were highly porous as well. Some were close to 500 meters squared per gram for these doped COFs. And we had both the fluorescence and the phosphorescence co-present. So we could use fluorescence as an internal standard where it doesn't change with the amount of oxygen, and phosphorescence was changing with the oxygen level. And we could track this and make a plot of oxygen sensing, so to say, using this covalent organic framework. We were surprised to see 8 orders of magnitude linear, this is a logarithmic scale, of course, correlation with the oxygen level from 10 to minus 5 torrs all the way to 1,000 torrs of partial pressure oxygen. After this work, there were a few reports of phosphorescence COFs that I found through them citing us. One of them was a sort of serendipitous discovery in a rigid hydrogen-bonded covalent organic framework, and one of them was through external doping inside the cavity, not in the framework itself. But there's still some challenges left in the field. What about undoped phosphorescent COFs, where we can actually tune or engineer the phosphorescence of the framework? It's not just a one COF that we have no design over, right? What if we want to make a pure COF that's phosphorescence? How can we reduce the triplet annihilation in such systems where we can maximize the amount of triplet emission without the cost of triplet annihilation? How can we have higher surface areas? 500 is in the lower range of covalent organic frameworks. There's many more porous compounds. In fact, recently our students who are sitting at the back synthesized a COF that is nearly 3,000 meters squared per gram of porosity. So this is an ongoing research now in my research group, where we started working on 3D COFs now, essentially getting inspired by the phenylene diboronic acid 2D COFs, trying to convert it into a 3D COFs, which are known when we have a carbon there, but not through transesterification. And people could not make anything more than silicone in there because the boronic acids become really difficult to work with and insoluble. Now, using our transesterification method, we already generated germanium-based. So germanium is here in the center, as a tin-based COF as well, the silicone and carbon, obviously. And we found that one of the COFs, so this is the result from last week. We don't have the full spectra yet, but it clearly has phosphorescence at room temperature, but under high vacuum. I have to put it in an EPR tube, suck the hell out of the tube to be able to see the phosphorescence ever so slightly. So we are now looking for collaborators. That's why I presented this slide. Anyone who has a solid state spectrometer that especially we can do different gases infused into the system, I'm very interested to work with and study these in more details, especially working on xenon, krypton. If you know anyone around, just send me there. And this kind of wraps up the PhD work that I had. And the second part of the talk is going to be about my postdoc project. That sort of branch out of this transesterification idea that we developed the reaction, and we made an almost difficult or impossible macrocycle in my postdoc, and we found that it has very high lithium affinity, somehow the most efficient lithium ionophore reported to date. Porphyrins and crown ethers are two of the pillars of supramolecular chemistry. Essentially, if you open up any paper or any book of supramolecular chemistry, you see some sort of structure having elements of crown ethers or porphyrins. These are macrocycles, one of which is a flexible macrocycle with hard oxygen bases inside the cavity, which allows us to bind to alkali or alkali earth metals. The other is a very flat and rigid molecule, even conjugated in the case of porphyrin, but because of the nitrogen soft bases, it only reacts with transition metals. Almost no alkali or alkali earth metals can be selectively bound to the center of it. But this flexibility of the crown ethers also reduces the selectivity of these crown ethers. Because now they're flexible, they can point the oxygens outside the cavity and have sandwich complexations, for example, forming with solvents, with another crown ether. Even the most well-known 18 crown 6 for potassium absorption or potassium binding, it's known to have 35 different crystal structures reported for many different metals. Even in the textbooks, you can see lithium, sodium, even potassium have different type of binding to the crown ether. Rubidium, cesium, essentially it's non-selective. Yeah, of course potassium goes in, but non-selectively if you have other ions present in there. And people have tried to really fuse this idea of rigidity and size selectivity with the crown ethers to enhance this sort of binding, but then the system becomes so complex that it's a whole own field of complex pathway studies for these supramolecular interactions that occur. So when I started my postdoc, this was the idea that Mark baked for almost 15 years in his group. He tried to make a macrocycle that he wanted to call it borphyrin. It's a portmanteau for porphyrin and having boronic acid in there, so hence borphyrin, right? I think he put it even in his discovery grant at the time that he wants to make a compound called borphyrin. But for 15 years, he tried with many different students, and this macrocycle was not solvable, essentially, to be formed. The original pursuit of this macrocycle was for its structural beauty. It's a macrocycle made from one single precursor that tetramerizes or wraps around itself to make a macrocycle. So you can think of this being essentially a condensation of boronic acids and the catechol on the same benzene ring. And that's in the field known as a head-to-tail assembled macrocycles. Many macrocycles, they're made from boronic acids on one moiety, catechols on another moiety. You mix them together with the right symmetry. If you're lucky, you'll get the macrocycle. But this was all in the same precursor, one compound to make the macrocycle. Some sort of quater Ouroboros, if you may, to make this macrocycle, right? And boronic esters have been known to make cages and macrocycles before, but again, through multi-component assembly, not through a head-to-tail assembled structure. And it was fundamentally difficult because when you have boronic acids and catechols on the same benzene ring, you can imagine many pathways that can go wrong and not form the macrocycle, let alone the polymerization and everything else. Boronic acids are really difficult to work with. They spontaneously oligomerize into dimers and trimers. If you leave them on bench, the water molecules would just get released. They react with protic solvents to make boronic esters. Protodeborylation, especially in such electron donating systems, is very prevalent as well. And the catechol has its own problem of catechol oxidation. You've seen in the case of hexahydroxyterphenyline how it was turning into a black-violet mess on the bench in the oxidized form. So imagine having all these problems on a single precursor that you want to then react it to make a macrocycle. And Mark found this was the master thesis from his student in 2015, that regardless of what sort of substitutions they put on this molecule, as soon as they wanted to take these protections out, proto-deborylation is the main pathway that goes wrong. So they end up with a cleaved boronic acid instead of a macrocycle. Right time and right person, so to say. When I had this transesterification in my mind, I tried it on a acetonide protected macrocycle, and I chose acetonide particularly because in slight acidic conditions, it can easily come off and turn into acetone, right? Which is then non-reactive with the catechol anymore, and it doesn't bother the boronic acid, so to say. And I did a borylation with BPIN group. Then using my transesterification developed method, we could make this macrocycle in near quantitative yields and then easily purify it through sublimations. No proto-deborylation was occurring. You can see this was, of course, a optimized reaction condition. We could just have the compound inside chloroform, add a little bit of acid. This acetonide would come off slowly, and then methyl boronic acid would react with the pinnacle to cleave, and macrocycle crashes out of the reaction. We could make it in very large scales now. Again, almost quantitative yields. This yield is after sublimation, so we lose some during the purification process. Surprisingly, it was very stable. So even though the precursor looked very fragile to work with, once the macrocycle forms, we could just put it in a test tube, heat it up with the torch in air, and it forms into it makes this nice white smoke, which you might think is burned, but it's the macrocycle kind of turning into a crystalline fog that then sits on the walls of the test tube. I can dissolve it in chloroform and study it as a pure compound. We then crystallize it. We looked at the crystal structures to just confirm that it's really the macrocycle, and we found it's as flat as we expected. We have this nice cavity inside, and we put different derivatives, of course, to make it more soluble and sort of easier to work with. The next question was, what can we do with it? So I started looking at some basic density functional theory calculations, just put a metal ion inside and let the system relax and see what happens. We found that only lithium stays inside. As soon as we change into sodium or anything bigger, the macrocycle has to bend to still have a maximum interaction. And this bending, even though it may occur in the gas phase, in solution it looks almost impossible because you have to bend these boronic acids and phenyl rings and twist them out of things. So we thought, well, I don't need to convince you perhaps why lithium is important. I just showed some applications here. Of course, most of it is for lithium-ion batteries. But some interesting applications are in dental crowns, and lithium seems to be one of the prime sources of tritium nuclear fusion in future. But it has to be ultra pure to be able to work with such lithium application. And it's surprising that 99.991% of lithium reserves on Earth, they are inside the oceans, and we have no access to them. The amount of lithium that we are scavenging essentially from the Earth crust are now in the tiny fraction of the lithium reserves on Earth that we have access to. And it's mainly focused in a small region in the world. There's many stories about overexploitation, sustainability of such systems. But imagine having access to ocean water, essentially sea salt, being able to extract lithium from such systems. Essentially, we can democratize access to lithium for any country that has access to ocean water, right? There's a big challenge, though. There's a big penalty we have to pay to extract lithium out of its crystal form. They have very high lattice energies in their salts, and especially they have very high hydration shell energy essentially around it. Lithium has this tiny space with one positive charge, so there's a big hydration shell around it. Any macrocycle who wants to go and grab this lithium to extract it selectively has to break through this hydration shell or break through this crystal lattice energy. And the best lithium ionophores that are reported to date, they have nearly 20 specificity to sodium versus to lithium versus sodium, meaning that if you have tens of thousands of ppm of sodium and magnesium and strontium and calcium inside the sea salt or seawater, the brine, it might not even touch lithium at that low concentrations of 0.1 ppm or so. So it was important for us to see whether now we can enhance the specificity of lithium absorption using the system. So I started looking at the NMR of the macrocycle, essentially titrating it with lithium. We could clearly see a shift of the NMR peaks corresponding to the macrocycle. So it was binding there, doing something. We didn't see this shift for any other metal ion that we added to the system, neither sodium, magnesium in very high concentrations, 500 equivalents almost. But we had to put almost 20 equivalent of 12 crown 4, which is one of the most well-known lithium binding macrocycles, to be able to now extract back this lithium from the macrocycle. So we had close to 20 times more binding affinity to the lithium with this macrocycle as compared to the conventional crown ethers. We studied different methods to make sure it's a one-to-one complex. What would be the binding constant? We found that it's in the orders of millions in ether, which is one of the highest numbers reported for lithium absorption in etheric solutions, for lithium binding. It was so high of binding to the lithium that we could add lithium fluoride, one of the most insoluble salts, lithium salts on Earth, and just adding an etheric solution of macrocycle on top of that, we could extract the lithium from the surface of these solids and turn it into a sort of gel, because the fluoride was also interacting with our porphyrin at the time. But this also happened for lithium chloride. We could look at the solution of the porphyrin and then add any type of different crystals of lithium salts. Even though they're very insoluble in organic solvents, the macrocycle can selectively go and bind to these and extract it from the salt crystal. We also did a test with many different soluble salts, where we can now control the concentration. It's not just a bunch of crystals added into a vial. We found that a sequential addition of potassium, rubidium, cesium, even an acid of this counter ion, we use this counter ion for solubility, and sodium, no change occurs or little change occurs to the UV vis of the macrocycle. As soon as we add one equivalent of lithium TDDS into the system, we see the whole absorption shift. So we sort of got greedy. I made a cocktail of many different salts without the presence of lithium and with presence of lithium. And we chose these to be sort of mimicking lithium waste, the lithium battery waste, or the sea salt. And we were delighted to see that there's only a tiny, tiny shift when we add the cocktail without lithium. And as soon as the salt cocktail with lithium chloride, even though it's a salt, it's not dissolved in solvent or anything, we clearly see a big shift. And later, the PhD student that was working with me found that this small shift here is not because of binding to the other metal ions that we have. It's perhaps because of the tiny amount of impurities that we had already in the other salts of sodium and potassium and rubidium that we were working with. So we took this one step further. We thought of now a way to extract lithium from mixture of different salts. Presumably, the best case scenario would be the sea salt. We just take the etheric solution of the porphyrin, add a bunch of crystals, including the lithium chloride crystals in there. We shake them together. We take the supernatant out. We filter and add it to an acidic solution or aqueous solution. Lithium goes to the water phase selectively, so we can extract the lithium out of that crystal, that mix of crystals that we had. And then we were hoping to get the macrocycle back, but what happens is the macrocycle breaks and proto-deborylates as soon as the complex touches water in presence of lithium. We think it's the acidity of the lithium that sort of catalyzes the proto-deborylation. We also looked at the flame test. So just a simple test, essentially taking dissolving the cocktail inside water and put it in the flame to see the color, and the extracted water that presumably has only lithium inside, and we could clearly see the red hue getting much more enhanced. Even visually by eye, we could see lithium binding essentially. And then, of course, we went to ICP. We again saw the same trend. No other metal ion was getting extracted from these salt cocktails. What we noticed was when we had magnesium sulfate and other sort of desiccant salts inside the cocktail, the lithium absorption capacity in the time frame that we optimized comes down. So we had a hypothesis that maybe it's a water assisted, like you need a little bit of water inside this etheric solution to be able to extract the lithium from the crystals. But there is still many open questions for this project that needs to be answered. The water stability, can we fix the water stability of these? Can we do sea salt lithium extraction? Can we do lithium battery recycling with these macrocycles? This is an ongoing question that we're trying to fix. And just to finish up the talk, I would like to show you sort of what we are now onto in my group. So we have 4 PhDs. One is still waiting in Iran for his visa, and 3 that are sitting at the back of the room, and 2 master students, one with Antonella co-supervised. And we call ourselves molecular architects. So we're interested in the structural beauty of organic molecules, how to assemble functional organic molecules into frameworks, cages, symmetric structures, being porous, and studying how they interact with the world around them. I hope I showcased some of the research interests that I had throughout the years. And now we're taking this one step further with the help of Ivado and Institut Courtois, and Mohammed from UFT, Professor Mousavi, to see if we can now leverage the use of Bayesian optimization and high throughput screening and also AI modeling of these frameworks to be able to optimize properties, for example, say phosphorescence or CO2 absorption, any sort of characteristic that we're looking for. And I showed this scheme here to sort of show the identity of the group that we are still building over time. And I'm very keen for any collaborations, any ideas that you have. And I would like to thank again all the funding agencies, my PhD and postdoc supervisors and teams, and my group that some of them are present here today as well. And I'm happy to answer any questions.